In the previous chapter, we've talked a lot about resistors. In this section, we will talk about two new electrical components. We will talk about capacitors and we will talk about inductors. Now, we will examine both of these electrical components in series and in parallel, and we will draw some similarities between capacitors, inductors, and resistors. We will now look into two different elements here. So what we'll be looking at is both a capacitor and inductor. And both of these are called passive elements because they do not generate energy. For example, a voltage source is active. A voltage source is active. This capacitors and inductors are not active. They are passive. They are passive components, and they're used as storage components. Storage. So they save energy that can be used at a later time. So that is what we'll be covering in this chapter. And I want to first go into talking about capacitors. So let's talk a little bit about capacitors. And capacitors are nothing more. We can simplify these as, let's take a look here. See if I can draw a capacitor. Okay, copy. We can think of these as just two plates, and these will have a certain amount of charge on them, negative and positive. And the same goes for this one, negative and positive. And these are plates. So just metal, they can be aluminum, copper, anything. And then there's space separating those two plates. There's just a little bit of space. So what happens here if we take this plate and take this plate and we connect it to a voltage source, so some sort of voltage source? Well, because this is positive here, this is positive, it attracts the negative components start moving this way. The negative charges start moving this way towards the positive. And on this side, we have the positive moving this way. So when we connect a voltage source up to this, let's see here, what we get, let's see if I can copy and paste this down here. So these move, and what it becomes is we get positive charges here and we get negative charges on this side. And if we take the voltage source off, if we turn this off, the charge on each of the plates, the charge will stay. So it is storing charge. And the voltage across here, the voltage, let's erase this. The voltage across the plates is equal to the voltage that we placed in between here. So this voltage is equal to this voltage after a specific amount of time. So in capacitors, we have these two plates, plate 1 and plate 2, and we call these electrodes. Electrode. This is an electrode, and this is an electrode. And between these two plates, in between these two, we call that the dielectric. Dielectric. And the dielectric can be air, nothing in between there, but also we can put other different types of material in here, such as ceramic material, and that is a very good insulator. It's an insulator that does not let current flow through. Ceramic, or even paper, just paper. So just paper in between those two. So that's what we call the dielectric. And if we take a look, this is a capacitor, and it has a coating on it, a protective coating. On the inside, we have two electrodes, one connected to each wire, and then in between the two electrodes, in between, we have a ceramic disc, is the dielectric. Okay, so maybe you've seen capacitors like this. Now this capacitor here is a little bit different. So we have the electrode, so I'll call this the electrode. We put our dielectric here. So this is our dielectric. Dielectric. And that prevents the current from flowing. This insulates. And then up here we have our other electrode. And then what happens is this is rolled up. So we roll this up, and that's what happens. This is the capacitor. So this is all rolled up into this here. And let's see if I can find an image of this real quick. So this is what happens when it is all rolled up. So then we get the capacitor here. So the charge on a capacitor, if we have a capacitor, we have two plates. And we connect those to a voltage source. Voltage source. The voltage source is here. The charge, Q, this is charge. Charge is equal to the capacitance C, times the voltage, And the capacitance is measured in a unit. The unit is farad. And we write it as a capital F, farad. So here we have the unit. So what impacts the amount of capacitance? Amount of capacitance. So one, it's the surface area of the plates. So if these are bigger, they have more capacitance. So if the plates are bigger, they have bigger capacitance. And in addition to that, the spacing of plates. So how far these plates are apart impacts the capacitance. And addition, the last one is permittivity of the material. Permittivity of material. So the material that it is made of, the material. So the capacitance is equal to the permittivity of the material, times the area, how big the plates are, and then divided by D, the distance, the spacing of the plates. So we have the area, the spacing, and the permittivity. So if the plates get closer together, D becomes smaller and the capacitance goes up. If the area gets bigger, the capacitance goes up. If the permittivity goes up, the capacitance gets bigger. So all of these impact the amount of capacitance in a capacitor. So let's talk about what is capacitance. Capacitance is equal to the total charge per volt. So the charge per volt. So if we have the capacitance equal to 1 coulomb, and I'll write out coulomb here, coulomb per 1 volt, 1 coulomb per 1 volt is equal to 1 farad, 1 farad. And that is our capacitance. Now, a lot of our capacitors will be in microfarads. Microfarads is a common capacitor size. Right? So a lot of times we'll measure things in microfarads. Okay, so that is what is a farad and how we can get the capacitance from the amount of charge and the voltage across that capacitor. Now, if you take a look and you remember, we said that the charge is equal to the capacitance times the voltage. And if you remember, dq dt, the change of charge with respect to time is equal to the current, So if we take the derivative, of the left-hand side, and we get dq dt, and then we take the derivative of the right-hand side, we get dv dt here. So we can say the current dq dt is equal to the capacitance times the derivative of the voltage with respect to time. We call this the derivative of the voltage. This is the voltage with respect to time. So this is current. Current is equal to the capacitance times the derivative of the voltage with respect to time. And likewise, let's get another sheet here. If we want to find the voltage as a function of time, we can take 1 over the capacitance and we integrate here from negative infinity to time t of I with respect to time. Okay, so this is nothing more than just integrating this equation. So we have I equals c dv dt. Okay, so if we move the c to the other side, we get 1 over c times I equals dv dt. And lastly, if we integrate both sides, well, let's move the t to the other side. So moving the t to the other side, and then we integrate both sides. Okay? Integrating this side, we bring out here, we get I dt equals, this would just be v, okay, as a function of t. So what we have here, that is this equation right here. That is this equation. So we can integrate the current and use the capacitance to find the voltage across those two plates. And the power is equal to the voltage times the current. Okay? But we said for a capacitor, this is C dV dt. Okay? So if we want the power for a capacitor, that can be equal to C times V times dV dt. And this is the power for a capacitor. Now there are several important factors. So important. So if voltage across capacitor is not is not changing, if the voltage is not changing, it is staying the same, then I, the current, must be equal to 0. And if you remember that I is equal to C dV dt, if the voltage is not changing, this is 0, and then that means the current must be 0. The current must be 0 as well. So if the voltage across the capacitor is not changing, then the current must be 0. That's important to know. 2, the voltage on a capacitor cannot change quickly. So the voltage across the capacitor cannot go from 0 to really big really quickly. It's a gradual change because the charge is building up and up and up. So it's a gradual. It cannot change quickly. Okay? We usually talk about ideal capacitors. Ideal capacitors, meaning they're perfect. They are perfect capacitors. And they do not dissipate energy. Okay? So they store energy and then they can return energy to the system, but they do not leak. They are perfect. They store the energy all the time. Okay? And lastly, but not all capacitors are perfect. Okay? So if you put a charge on a capacitor, take the voltage source off, you hope that the charge stays there forever and ever and ever. But what ends up happening over time is the charge starts to leak. It starts to go away, okay, over time. And that is a case of a non-ideal capacitor. Non-ideal, not perfect. So these are important things that you should remember when talking about capacitors. Now let's talk about these things in series and parallel. So if you remember, if we have, let's say we have a current source here. And we have resistors. These are 3 resistors. And let's say that these are R1, R2, and R3. We can add those together for an equivalent resistance. And we have been doing this a lot, R1 plus R2 plus R3. Now let's take the same circuit, and this time we have capacitors, and this is how we draw capacitors. And so this is C1, C2, and C3. So if we want the equivalent capacitance, we could go C1 plus C2 plus C3. Is this right? This is wrong. Incorrect. Wrong. If we want the equivalent capacitance, we must add them together like we do resistors in parallel. So if these are in series, we add them together like resistors in parallel. So we have the equivalent capacitance is equal to, equal 1 over C1 plus 1 over C2 plus 1 over C3. Okay. So we must add these together like resistors in parallel. Okay, so we have this sort of thing. Now let's talk about how do we do it if we have capacitors in parallel. So we have capacitors in parallel, C1, C2, C3. Now, if we want the equivalent capacitance, we add them together like resistors in series. So these are in parallel. Parallel. So this is equal to C1 plus C2 plus C3. So we must remember that it is opposite of how we add resistors together. So remember, combining capacitors is the opposite of how we combine resistors. Okay, so remember that because we'll be doing a lot of problems with capacitors. Now that we've talked about capacitors, we will now move to talk about inductors. Inductors are another storage device. They are passive. They do not generate energy. They're passive, and they store energy in a magnetic field. So let's take a look here at different inductors. So these are all inductors. So inductors. All inductors. They are sometimes called coils. They are also called coils and sometimes called chokes. Both names for inductors. So coils because it is a coil. This is a coil. And also chokes. Chokes. Like I'm choking. Chokes. So they're called both coils and chokes. And this is what they look like. Now, the inductor here, if we draw the inductor like this. This is the inductor. And we have a certain amount of current, I, and we can label the voltage across here as V. And this is the inductance, which we label with the letter L. Inductance, L, with the letter L. And the inductance is equal, or let's put it this way. The voltage is equal to the inductance times di dt. So if this is I, this is how it is changing with time. So the voltage varies with the change in current. Okay. So we can use this equation. Additionally, L is equal to this value, N squared times mu times A times divided by L. Now this, let's take a look here. Let's get a diagram. Okay. So as you see here, let's make sure you can see that. So N is the number of turns. So it is 1, 2, 3, 4. That is N, the number of turns. A is the cross-sectional area, how big that is, the area. And L is the length, so how long it is. How long that is L. And lastly, mu here, the Greek letter mu, is the permeability of the core, So that really depends on what is in the middle. What material is in the middle. That is mu. And this is then our inductance that we put into our equation for L here. So that is just a brief introduction to inductors, which we also call coils or chokes. So as we think about inductors, we draw them as coils here, and we may label them L1 for inductor. The unit we use, the unit is Henry, Henries, which is a name, Henries. So in use, we may have microhenries for things like electronics. So we may use inductors with microhenries in our phones. But if we have very big inductors, we measure those in henries, right? Micro meaning small, that is 10 to the negative sixth. And then we have henries, which is very big for power systems, for very big power systems. Okay, so when are inductors helpful? So if you remember, the voltage here is equal to L di dt. This is the change in current with time. The change in current with time. Let's take a look at an example where we have a house. So this is a house. And inside we have a laptop. A laptop computer. And we have this laptop plugged into the wall here. Now outside it is raining, and a big lightning bolt hits the house. Very big lightning bolt hits the house. Now that electricity here goes in and goes up to your computer. And what happens? What happens? Well, it will probably break your computer and maybe have a fire, right? So this would be bad. This would be bad. So what is going on here? Well, this current is going very fast into your computer and causes heat and makes a fire. Okay? So what we can do here is right here, we can put a inductor. If we put an inductor right here, and it will, a big inductor, if we have big inductance, and the voltage is very big, so this is here, we have a big, very large voltage. We can slow down the current. So if we have a big inductance, if this is also big, this can make this low or small. It can make this small. So if the change in current is small, then we don't break our equipment. This does not happen. And if you take a look at these, this is what we call a surge protector. And these have, among other things, but one thing that they have on the inside is inductors. They have inductors on the inside here, and it prevents a surge, meaning a fast surge, right? A surge of electricity. And so it protects. It keeps things safe. It protects from a large surge. So we use inductors. We can use inductors to slow down the change of current. We can slow down the change of current by doing that. And it stores all of this energy in a magnetic field. Stores the energy in a magnetic field. Now we've said that the voltage of an inductor is L di dt, but we can also find the current here if we then move the L to the other side. So if we move L to the other side, we get 1 over L times V equals di dt. Okay, and then we can integrate both sides, and the current is 1 over L, and then we can integrate from the start time, the start, to the end time, times the voltage as a function of time, the voltage as a function of time, dt. And then we must add on to here the initial current at time 0. So as you integrate, remember that you find a C, right? This is our constant plus C here. So we must add that on to the end here. So when we integrate, we must add on the plus C. And we can use these two relationships to solve for inductors. Next, let's talk about series and parallel for inductors. So let's first put our inductors in series. So this is series, and we can label this L1, L2, and L3. Now, if we want to combine all of these to a single equivalent inductance, how do we add these together? How do we do it? Well, these add together just like resistors, the same as resistors. L1 plus L2 plus L3. Now let's talk about these in parallel. So in parallel, we have inductors in parallel. All right, this is L1, L2, and L3. To get the equivalent inductance here, we add them together just like we add them together just like resistors in parallel. Just like resistors in parallel. So we have 1 over the equivalent inductance equals 1 over L1 plus 1 over L2 plus 1 over L3. So we add them together like resistors in parallel. So we will use this to solve for the equivalent inductance. Now let's finish up by doing some comparisons between capacitors and inductors. So let's take a look, and I'm going to make 2 columns, capacitor and inductor. Capacitor and inductor. And remember, for a capacitor, we have the current is equal to the capacitance times dV dt. Now for the inductor, it looks similar, except we have the voltage is equal to the inductance times di dt. Okay. So you can see the difference between these two. Furthermore, we have the voltage at time t for a capacitor is equal to 1 over C times the integration from initial time to final time, I as a function of time, this tau means time, plus V at time 0. Okay, this is the plus C, remember, when we integrate. So we have the voltage for a capacitor. Now for an inductor, we have the current, which is equal to 1 over L times, or the integration of from T naught to T, the voltage with respect to time, plus the current at time t0, at the current time. All right, so you can see the relationship here. Furthermore, if we add we have C1 and C2, we add these two together. Remember that the equivalent capacitance is equal to 1 over C1 plus 1 over C2. And if we have inductors in series, L1 and L2, the equivalent inductance is L1 plus L2. Okay. And furthermore, we can move to parallel. If we have capacitors in parallel, C1 and C2, the equivalent capacitance is C1 plus C2. And lastly, for inductors in parallel, L1 and L2, we have the equivalent inductance is 1 over L1 plus 1 over L2. Okay, so you see the relationship between the capacitor and the inductor. And they both store energy. The capacitor stores energy in an electric field. The inductor stores energy in a magnetic field. Okay, so there are differences, but they both can store energy and they are both passive devices.